Very good evening, everyone. So, as you know, hope you are very well. So, as you know, that today we are going to study about electrochemistry, next part, which is part 5, right? Previously, we have covered first, second, third, fourth part of the theory of electrochemistry. Today's topic is NCRT Chapter 2, Electrochemistry Theory Part 5. Let's start. Disclaimer. The images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of original creators and owners. If you are the owner and have any concern or issue, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using the generative AI, which is experimental. So, today's objective of the class is that after attending this lecture, you will be able to justify the variation of conductivity and molar conductivity of the solutions with change in their concentration and define lambda naught m, which is molar conductivity at zero concentration or infinite dilution. And then you will be able to enunciate Kohlrausch law and learn its applications. So the topics which you have to be covered, we will going to cover according to the NCRTR. The first is 2.4.2 subsection, which is variation of conductivity and molar conductivity with the concentration. So in this, first of all, we will study about the molar conductivity, then the limiting molar conductivity, then about strong electrolytes, then Kohlrausch law we will cover. Then we will talk about the weak electrolytes. And then lastly, we will cover the applications of Kohlrausch law. And then we will see some examples and Intext question at the end. Okay. So these are the topics we will going to cover. As the definition says that molar conductivity for a solution at the given concentration is the conductance of volume V for the solution. So basically for a solution at its given concentration. So concentration you can define it in the terms of molarity, and molar conductivity is the conductance of that solution which is having a V volume and containing a 1 mole of electrolyte which is kept between the two electrodes with the area of cross section A and distance of unit length. Unit length means the length between the electrodes we are taking as 1, and the cross section of area of the two electrodes we are taking as A, and the two electrodes are kept between the two electrodes are kept in the solution which is having the volume V, and it is having 1 mole of electrolyte in it. The solution has 1 mole of electrolyte. So the conductivity of that solution is defined as the molar conductivity. Therefore, you can say that the lambda m, okay, m is representing the molar conductivity. So lambda m equals to kappa A by L, or you can also write it as kappa if you take A and L both as unity or 1. Okay. So molar conductivity is defined as kappa times A by L, or in the case of unit length and area, it will be equals to kappa. Now since length is 1 and area is equals to V, area will become V. V is volume which is containing 1 mole of electrolyte. Because as I said that volume is defined as area times length, right? Length we are taking 1, so volume will become equals to area. So del lambda m, that is molar conductivity, will become equals to kappa V. Okay, because this term A by L, L is 1 and A become equals to V volume. So lambda m molar conductivity is equals to kappa V. Okay. Now this equation is equation 2.22 in our NCRT textbook. Next, we will cover limiting molar conductivity. So, molar conductivity, as I said, lambda m increases with the decrease in the concentration. So, for a given solution, if you decrease the concentration of the solution, the molar conductivity of that solution will increase. Why? This is because the total volume V of the solution containing 1 mole of electrolyte is also increasing with the decrease in the concentration. Okay, so the molar conductivity increases with the decrease of the concentration. Why? Because the volume, the total volume V of the solution, which contains 1 mole of electrolyte, is also increasing. And it has been found that the decrease in the kappa on dilution of a solution, that is the decrease in the decrease in conductivity on dilution of a solution, is more than the compensated by increase in its volume. Okay, but here we are doing comparison, that it has been found that if you decrease in the conductivity on the dilution of a solution, okay, when you diluting the solution, diluting means you are adding more and more solvent part. So when you are diluting the solution, so the decrease in the conductivity will happen, which is more compensated by the increase in its volume. Okay, which is more than compensated by it by the increase in its volume. Volume is also increasing on the dilution of the solution. Okay, but this thing, that the conductivity is decreasing, this will be compensate by the increase in the volume of the solution. It means that at a given concentration, the molar conductivity can be defined as the conductance of the electrolytic solution, which is kept between the electrodes of a conductivity cell at unit distance, but having the area of cross section large enough to accommodate sufficient volume of solution that contains 1 mole of electrolyte. Okay, so we are defining the molar conductivity again, that at a given concentration, at a known concentration of the solution, the lambda m, that is molar conductivity, uh, is defined as the conductance of electrolytic solution. Electrolytic solution means a solution which is, having the electrolytic solution, and it is having a beaker having electrolytic solution. It is having the electrodes dipped in them, and they are connecting by the wire through which the current is flowing. Okay, so we are defining the conductance for this solution. The molar conductance for this solution can be defined as the conductance which is kept this of the solution, which is kept between the electrodes. These are the electrodes, right? So this solution which is kept between the electrodes of a conductivity cell at unit distance, and the distance between these two electrodes are unit, that means 1 meter you can consider, but having area of cross section large enough to accommodate sufficient volume of solution. But their area of cross section, that means this area of cross section between the electrode, is large enough to contain sufficient volume of the solution, sufficient amount of the solution that contains 1 mole of electrolyte. So this is the new definition for the molar conductivity. When the concentration approaches 0, the molar conductivity is known as limiting molar conductivity, as the name suggests, limiting. That means something is very smaller, something is decreasing very, very much, that it is approaching to the 0, right? That we only have it in limit. So when the concentration approaching 0 value, okay, when the concentration is approaching 0, the molar conductivity for an electrolytic solution is known as limiting molar conductivity, and the symbol we used it for representation is lambda naught m. Just nothing in the molar conductivity symbol we put here a naught. Okay. And so strong electrolytes, if you asked about the strong electrolytes, which comes under the topic or subsection 2.4.2, we define it that for the strong electrolytes, the molar conductivity, that is lambda m, increases slowly with the dilution and can be represented by the equation. Okay, so strong electrolytes, for the strong electrolytes, this molar conductivity value increases with the dilution. If you are diluting the solution, the molar conductivity will increase, and it can be represented by the equation lambda m equals to lambda m naught minus AC to the power half. Okay, this is the NCRT equation 2.23 given in our NCRT textbook. This is molar conductivity in this equation. This is limiting molar conductivity we just have discussed. And C is concentration, and its power half means we are taking the concentration in the under root. Okay. So, where this is molar conductivity, lambda m is molar conductivity. Molar conductivity, we just have defined that the conductivity of a solution in which 1 mole of electrolyte is present. Okay. Then lambda naught m is limiting molar conductivity. That means when the conductivity of a solution is approaching 0, that for that solution, the conductivity is referred to limiting molar conductivity. Okay, when the concentration is approaching 0, then the conductivity of that solution will be limiting molar conductivity. Okay, A is also a thing. A here is a Debye-Huckel constant. Okay, this is a constant. A is a constant, and it has a name which is Debye-Huckel constant. And C is, of course, as I said, concentration. Okay, so this is under root of C. You can also write it as lambda m naught minus A under root C. Okay, so this can be also written as lambda m equals to lambda m naught minus A under root C. Let's continue. So, continuing to the strong electrolytes, this is a graph, and this is figure 2.6, which is representing the molar conductivity versus the C half. That means the under root concentration. Potassium chloride, strong electrolyte in the aqueous solution. So this graph is the molar conductivity versus the concentration graph for the strong electrolyte. Let's suppose we are taking here potassium chloride, KCl. Okay, so this is a graph. The y-axis is representing lambda m, which is molar conductivity in the Simon centimeter square mole inverse units. It has given two values for that, 200 and 400, marked on the y-axis. On the x-axis, we have taken the C power half, or you can also take it as under root C, under root of concentration in the mole per liter. Okay. And if you observe for the strong electrolyte, we are obtaining a straight line in a decreasing slope. Okay. So you can see we have this line representation, right? This is for the representation of strong electrolyte of molar conductivity versus the concentration graph for the potassium chloride. Now, it can be seen that if we plot, as we have plotted in the figure 2.6, the molar conductivity against the under root of concentration, we obtain a straight line with intercept equal to limiting molar conductivity. So this intercept is limiting molar conductivity and slope equal to minus A. The slope you will get for this line will be equals to minus A. That is minus of that Debye-Huckel's constant. The value of the constant A, this constant A value for a given solvent and temperature depends on the type of electrolyte. Okay, so the value of this constant A for a given solvent is depending upon the type of the electrolyte which is present in our solution. Okay, that is the charges on the cation and anion produced on the dissociation of the electrolyte in the solution. Okay, that's why we are saying that type of electrolyte. What is the type of electrolyte you are using? Either potassium chloride or anything else, sodium chloride. Okay, whatever you are using. So the charge which is present on the cation. Cation means the ion which is having the positive charge. For example, from the sodium chloride, we get sodium positive. So this is cation. And the anion means we are getting the ion in the negative charge. So chlorine, negative, chloride ion. Okay. So the A value is depending upon the type of electrolyte. That means the charges on the cation and the anion, which is produced by the dissociation of the electrolyte we are using. Okay. On that, the A value, the Debye-Huckel's constant value will depend on. And this is the graph we have seen for the molar conductivity versus the concentration graph for strong electrolyte. And we are considering here the potassium chloride. And we are obtaining a straight line with a slope minus A and the intercept of limiting molar conductivity. So, our next topic under the subsection 2.4.2 is Kohlrausch Law. The Kohlrausch Law states that the molar conductivity of an electrolyte at infinite dilution is sum of individual contribution of its positive and negative ions. Okay, so what we are saying that Kohlrausch law is a law which says that the molar conductivity, that means lambda m. Okay, molar conductivity of an electrolyte, let's suppose we are talking about KCl. Okay, so for an electrolyte, the molar conductivity at infinite dilution means we are increasing the content of the solvent in our solution. When the dilution become infinite, okay, at that position, at that term, that when you are reaching the infinite dilution, the molar conductivity of electrolyte is sum of individual contributions of its positive and negative ions. Okay, so for an electrolyte which contains both positive and negative ions like this, K positive and Cl negative in the case of KCl, which is a strong electrolyte, the molar conductivity of the electrolyte KCl at infinite dilutions is sum of individual contributions from the positive and the negative ions of the electrolyte. This is what Kohlrausch law says. An electrolyte on the dissociation gives V positive cations and V negative anions. Let's see. Okay, that when you take a electrolyte, when you dissociate it, so on the dissociation, it will give V positive cations and V negative anions. So the limiting molar conductivity, lambda naught m, can be represented by V positive for the cation multiply by lambda positive naught plus V negative multiply by lambda naught negative. Okay, so this is the equation 2.25 marked as 2.25 in our NCERT textbook. Okay, so where we can define the lambda naught positive and lambda naught negative limiting molar conductivities of the cation and the anion respectively. Okay, let me again tell you this. Just a minute. So this is what the Kohlrausch law states, that when you are taking a electrolyte, when you are talking about the electrolyte which our solution is made up of. Okay, so when you are talking about this and when you are talking about the molar conductivity of that electrolyte, so the electrolyte positive ions and the negative ions both will contribute equally. So the individual positive ion and the negative ion limiting molar conductivity sum will be equals to the molar conductivity of that solution at the infinite dilution. Okay, this is what is said by the Kohlrausch law. So if you see that this is we are studying, in the section under 2.4.2. So basically, so this is actually molar conductivity. Okay, this is molar conductivity, and these are the molar conductivity of the electrolyte, and these are the molar conductivities of the positive and the negative ions of the electrolyte. Okay, so don't confuse. And this is the representation for the cation and the anions. That this is number of cations, this is the number of anions, and multiply by their respective limiting molar conductivities. Okay. Continuing on this topic, the value of lambda naught for some cations and anions at this particular temperature, which is 298 Kelvin, are given in the table 2.4, which we're going to see. Okay, so the value of limiting molar conductivity of the cations and anions. So this is the table where we have given the ions like H positive, Na positive, potassium positive, calcium 2 positive, magnesium 2 positive, OH negative, chlorine negative, Br negative, CH3CO acetate ion, and SO4 2 negative sulfate ion. Okay, these are the different ions with their respective limiting molar conductivities value. So lambda naught in the Simon centimeter square mole inverse. So these are the value of the lambda naught. So for H positive it is 349.6, the largest among the given ions. For sodium positive it is 50.1, for potassium positive it is 73.5, calcium 2 positive 119.0, magnesium 2 positive 106, OH negative 199.1, chlorine negative 76.3, Br negative 78.1, CH3CO negative 40.9, and SO4 2 negative as 160. Okay, so these are the different values of anions and cations limiting molar conductivity. Okay, now we have talked about the strong electrolytes. Now what are weak electrolytes and what are their properties, how we deal with that in this chapter. So consider an electrolyte AB. Okay, C moles of which are dissolved per decimeter cubic of an aqueous solution. Okay, we take a we take a electrolyte AB. We are not telling right now that whether this is weak or strong. So we are taking just electrolyte AB. C number of moles of this electrolyte are dissolved per decimeter cubic of an aqueous solution. What does that mean? That for 1 decimeter cubic, we are dissolving C moles. For 2 decimeter cubic of solution, we are dissolving 2C of moles of the electrolyte. Okay. Now, let alpha be its degree of dissociation. Okay. Degree of dissociation means that in which amount, in which degree, uh, in which amount the electrolyte we have been taken, which is AB, is dissociating. Okay. Of course, if it is a AB, it is having a positive ion and a negative ion, right? Let's suppose A is a positive ion, so A positive and B negative. Okay. Now, what is the degree of dissociation of this AB electrolyte? That in which amount or how much this electrolyte is dissociating. Okay. That is fraction of total concentration of electrolyte. Okay, so the electrolyte total concentration fraction which we are obtaining is referring to the degree of dissociation which exists in the dissociated state. So let's see. Then you can say that alpha degree of dissociation will be equals to lambda m upon lambda m naught. That is molar conductivity upon the limiting molar conductivity. This is the formula for defining the alpha, that is degree of dissociation. This is the NCERT equation 2.26 present in our NCERT textbook. And this is the graph which is figure 2.6 representing the molar conductivity versus the under root C for the acetic acid, and which is a weak electrolyte in the aqueous solution. We have been seen the graph or the figure for the molar conductivity versus the under root C for a strong electrolyte, right? And for a weak electrolyte like acetic acid, we are obtaining this graph, which is a curve, right? You can see this is a curve. In the previous case, in the strong electrolyte case, we are obtaining a straight line. Here in the weak electrolyte case, we are obtaining a curve in this shape. You can see in the blue line, right? This is for acetic acid. I'm continuing on this topic. So let's suppose you have a reaction for the electrolyte which is dissociating in the A positive and B negative. Okay. The initial concentration, if you consider for each of the species, so electrolyte is C moles. Okay, we have taken the C moles of electrolyte. So initial concentration is C. A positive is 0 and B negative is 0 because it hasn't been dissociating yet. But at the equilibrium concentration, when the dissociation happens, the AB, that means the electrolyte concentration, will become C times 1 minus alpha. Okay, you can also write it as C minus C alpha. And the A positive will become C alpha and the B negative will become C alpha. Same amount of dissociation will happen for the positive and the negative ions, cations and the anions, right? So if A positive will C alpha, B negative will C alpha, that means C alpha amount of electrolyte is dissociating. Okay, so the equilibrium concentration of electrolyte will become, initial concentration was C minus the dissociated concentration, which is C alpha. So C minus C alpha is the equilibrium concentration of the electrolyte AB. And Ka, you can define it as C alpha square upon 1 minus alpha. Ka is the reaction constant. Okay, it will be the product upon the reactant, right? Product are A positive and B negative. So A positive and B negative divided by AB. This is for the expression of Ka, right? We know that A positive is C alpha. So C alpha times, again the B negative is also C alpha at equilibrium. So C alpha upon AB is C 1 minus alpha equals to K. So this is what it is written here. That's C alpha square. So basically when you multiply it, it will become C square alpha square upon C times 1 minus alpha, and the C will cancel out. So we will get C alpha square upon 1 minus alpha. Okay. Now alpha we just describe at del m upon lambda m naught. Right? The ratio of the molar conductivity and limiting molar conductivity for a solution. So we just put that ratio at the place of alpha, wherever alpha is. It will become C. So, okay, let me solve this. So, C alpha square upon 1 minus alpha. Okay, so C lambda m square upon lambda naught m square upon 1 minus lambda m upon lambda m naught. 1 minus alpha, right? Now we can take this lambda naught m square in the denominator because it will anyway go in the denominator. So C lambda m square upon lambda m naught square, and this is in the multiplication, lambda m upon lambda m naught, right? Now you can take here the LCM and then you can get C lambda m square upon lambda naught m square times lambda m naught minus lambda m upon lambda m naught, right? Here the lambda m naught will cancel out, right? One lambda naught will cancel out, and here in the denominator nothing will left, so only this quantity will left, and this will be equals to C lambda m square upon lambda m naught multiplied by lambda m naught minus lambda m. We just simplify this equation by putting the alpha value, which is lambda m upon lambda m naught. Okay, and we will get finally the relationship between the equilibrium constant, the concentration, and the molar conductivity and the limiting molar conductivity for a electrolyte. Okay, so for defining or for obtaining the degree of dissociation, that is alpha, you can use the solutions, molar conductivity, and the limiting molar conductivity. And this equation is marked as 2.27 in our NCERT textbook. Now let's see the applications of Kohlrausch law. Using the Kohlrausch law of the independent migration of the ions, it is possible to calculate the limiting molar conductivity for any electrolyte from the limiting molar conductivity of the individual ions. Okay, what we are saying, that using the Kohlrausch law, because the limiting molar conductivity of the individual ions is only given in the Kohlrausch law, right? Kohlrausch law, what Kohlrausch law said there, that lambda m naught equals to V positive lambda naught positive plus V negative lambda naught negative, right? So this term, this lambda naught term, that is limiting molar of individual ion, individual positive ion and negative ion, is only given in the Kohlrausch law. So using the Kohlrausch law of the independent migration of ions, it is possible to calculate this value because it is given in the left hand side. This value of limiting molar conductivity for a solution for any electrolyte from its limiting molar conductivity of its individual ions. The second implication is that, moreover, for the weak electrolytes, which cannot completely dissociate into the complete positive ions and the negative ions. So for the weak electrolytes like acetic acid, CH3COOH, okay, this can dissociate in CH3COO negative and H positive. Okay, so the weak electrolyte like acetic acid, it is possible to determine the value of its dissociation constant once we know the limiting molar conductivity and the molar conductivity at a given concentration C for a solution. Okay, by using the Kohlrausch law. Okay, now let's do an example. Example marked as 2.6 in the NCERT. This says that the molar conductivity of the KCl solution at different concentrations at 298 Kelvin are given below. Okay, so the molar conductivity means lambda m of the KCl solution at different concentration. That means C is different. At different C, we have different molar conductivity at this temperature, and it is given below, which is this. This is the C, that is concentration in the mole per liter, and this is molar conductivity in the Simon centimeter square mole inverse. These are the values. Okay. Now, show that a plot between the molar conductivity and the under root concentration is a straight line, and determine the values of the limiting molar conductivity and A, that is Debye-Huckel's constant for the KCl. Okay. So let's see. So if you take the square root of the concentration, okay, if you take the square root of the concentration, that means these values which is given in the decimal, what we will obtain? This table, okay, in which we have taken the square root of concentration because we have to make the graph between the molar conductivity and C half. Okay, C half means under root of concentration. So you have to take every concentration under root. So for this, the under root will be 0.01407. For this, the under root of the concentration is 0.01758. For the third one, it will be 0.02283. And for this, the under root of concentration is 0.03145. And the molar conductivity will be same as given in the question, okay, for every concentration. Now let's see the solution. So for a plot of the lambda m, okay, the plot of the molar conductivity, which will go on the y-axis, and the concentration power half, which will go on the x-axis, is shown in the figure 2.7. And this is the figure 2.7, which is the variation, which is giving the variation of the molar conductivity against the concentration under root. Okay, at the y-axis we have molar conductivity, at the x-axis we have concentration under root. Okay, you can see we are obtaining a straight line, okay, at different points, and these points are representing the concentration we just have in the table and their respective molar conductivity value. Okay, so the question says that show that the plot between this and this, that means molar conductivity and the concentration under root is a straight line. So we have showing that the graph between the molar conductivity and the under root of concentration is a straight line. Now, what we have to find out the value of limiting molar conductivity and the A constant for the KCl. So let's see that. For that, it can be seen that it is nearly a straight line, right? Graph was nearly a straight line, and the intercept C half equals to 0 from the intercept at C half equals to 0. Okay, concentration was at the x-axis. At the 0 value of the concentration, the intercept, we find that will be this much. Okay, this much, 149.8 or more. Now, lambda naught m is equals to 150.0 Simon centimeter square mole inverse. Okay, because we know the lambda m value from the graph. Okay, and through that we can consider the lambda m naught because we have different lambda m values. Okay, and A, which is giving as minus of slope, right? A is given as minus of slope because the slope for that straight line will be negative because the line was like that. The line graph was like that. Let's suppose this is x-axis and this is y-axis. If the line was like that, the slope will be positive, and we have y-axis and x-axis. If the line like this, as we have seen, then slope will be negative. So A is equals to minus of slope, and that will be equals to 87.46 Simon centimeter square mole inverse. Okay, so as we said that the Kohlrausch law graph, the applying the Kohlrausch law, the graph we can obtain for the weak electrolyte and strong electrolyte, and from that we can find out that what will be the limiting molar conductivity, which will be the slope, which will be the intercept of the graph, which is this. So lambda naught will be 150 because that 148.61, right? And greater than that will be 150. You just have to measure from the graph. Whatever the intercept will be, that will be the value of limiting molar conductivity. And the A value will be minus of slope, right? Or you can say slope value was, we have seen that slope value was minus of A. So A value will be minus of slope. Slope was in the negative, which is 87.46. So negative of slope will become negative, negative will become positive. So it will be, A value will be 87.46 Simon centimeter square mole inverse, or mole liter per under root of concentration unit, like mole per liter. Okay, so these are the values for lambda naught, that is the limiting molar conductivity, and the Debye-Huckel constant for our strong electrolyte KCl. And we have seen its graph. We have shown the graph that the plot between the molar concentration and the under root of concentration was a straight line. Now, let's see our next example, which is example 2.7. It says that calculate the limiting molar conductivity for the calcium chloride and magnesium sulfate from the data which is given in the table 2.4. So this is the table given. These are the ions with their respective lambda naught values. H positive, sodium positive, potassium positive, calcium 2 positive, and magnesium 2 positive. And similarly, OH negative, chlorine negative, bromine negative, acetate ion, and sulfate ion, and their respective lambda naught values. This is table 2.4, and you have to calculate the limiting molar conductivity for the calcium chloride and magnesium chloride using this data given in this table. So, as we know from the Kohlrausch law that the lambda naught m, that is the limiting molar conductivity for the calcium chloride, can be defined as the limiting molar conductivity sum of either of the ions, right? The cations and the anions, okay, and multiply by their numbers. So that the Kohlrausch law says that lambda naught m equals to V positive lambda naught positive plus V negative lambda naught negative. This are representing the number of anions and or the cations we are getting, and they lambda naught positive and lambda naught negative are representing the limiting molar conductivity of the cations and the anions we are getting after the dissociation of the electrolyte. Okay, so for the calcium chloride, the limiting molar conductivity of calcium chloride will be V positive. So for the calcium 2 positive, we have obtained only one calcium 2 positive. So 1 multiplied by lambda naught of calcium 2 positive plus the number of anions we obtain is 2 chlorine negative. So 2 times lambda naught of Cl negative. Okay, this will be the equation. And you know the lambda naught values for calcium 2 positive, right? Which is 119. And you know the lambda naught value of chlorine negative, which is 76.3. So you just have to put it here and add them. So 119 plus 2 times 76.3 will give the limiting molar conductivity of CaCl2. So it will be equals to 271.6 Simon centimeter square mole inverse. This is the limiting molar conductivity value of calcium chloride. Now we have to find it for magnesium sulfate in the similar way. So for the magnesium sulfate, the limiting molar conductivity will be equal to the multiplication of the product of the number of the ions we are getting for cation and anion and multiply by their limiting molar conductivities and their sum. Okay, so limiting molar conductivity of magnesium sulfate will be 1 multiplied by lambda naught of magnesium 2 positive, because only one magnesium 2 positive we are getting after the dissociation of MgSO4. So magnesium sulfate will dissociate into Mg2 plus SO4 2 minus. Right? In the previous case, in the CaCl2 case, it is dissociating into the calcium 2 plus 2 Cl minus. Okay, so as we were getting 2 number of anions, that's why we have multiplied the limiting molar conductivity of the anion chlorine with 2. Okay, so here in this case, magnesium sulfate, the limiting molar conductivity of magnesium sulfate will be this, and you know the limiting molar conductivity value of magnesium 2 positive, and for SO4 2 negative you also know the lambda naught. So you just have to add these two values. So 106.0 Simon centimeter square mole inverse plus 160.0 Simon centimeter square mole inverse, you have to add them, which will give the value of 266 Simon centimeter square mole inverse. So this is the limiting molar conductivity value for the magnesium sulfate. Okay, so the question asked was that you have to identify the lambda naught m for these two electrolytes, and you have calculated the lambda naught m value for both CaCl2 and magnesium sulfate using the lambda naught or the limiting molar conductivity of their cations and anions in both the electrolytes. Let's see the next example, which is 2.8. This says that lambda naught m, that is limiting molar conductivity for sodium chloride, HCl and sodium acetate, are 126.4, 425.9 and 91 Simon centimeter square mole inverse respectively. You have to calculate the lambda naught m for HAC. Okay, that means acetate. So you have to just divide, or for the HAC, that means CH3. This is nothing but, let me write it. Okay, this is CH3 COOH HAC. Okay, now for that you use the Kohlrausch law, and that will be equals to lambda naught of H positive plus lambda naught of AC negative, because it will dissociate into acetate ion CH3CO minus and hydrogen ion, right? So lambda naught of hydrogen ion, that is cation, plus lambda naught of acetate ion. Now this is single ion, but here in the acetate ion this can be more dissociate into different ions. So you can write it as lambda naught of H positive plus lambda naught of AC negative. So For the lambda naught of AC negative, you can arrange the different lambda naught of the ions, which you can get from the electrolytes NaCl, HCl, and NaAC, whose values are already given for the limiting molar conductivity. Right? So we write it as lambda naught of Cl negative plus lambda naught of AC negative plus lambda naught of Na positive plus minus lambda naught of Cl negative minus lambda naught of Na positive. Okay. Why we are writing it like that? We just see, because we are having the electrolytic, you know, this lambda naught m value, that is limiting molar conductivity value for different electrolytes, which is NaCl, HCl, and sodium acetate. So for the NaCl will dissociate into sodium positive and chlorine negative. Similarly, HCl will dissociate into H positive and chlorine negative. And the sodium acetate will dissociate into acetate ion and the anion and the sodium cation. Right? So how can we use these electrolyte limiting molar conductivity values to determine the limiting molar conductivity of HAC, acetic acid? So we write this equation using the Kohlrausch law, where the limiting molar conductivity of HAC is H positive plus AC negative limiting molar conductivities. And you can also write it in the form of H positive plus Cl negative, which will make the limiting molar conductivity of HCl, AC negative limiting molar conductivity plus Na positive limiting molar conductivity, which makes the limiting molar conductivity of sodium acetate. And in the negative, we have written the limiting molar conductivity of Cl negative and Na positive, which will makes the limiting molar conductivity of NaCl in the negative sign. Why we use the negative sign? Because this in the negative and this in the positive will cancel out because both are same. And this in the negative and this in the positive will cancel out because both are same. So we are writing this, we are expanding this, because we want to get this equation of the limiting molar conductivities of different electrolytes, for which the values of lambda m is given already in the question. Okay. Now we can simply write the values here. So lambda naught of HCl is given as 425.9. So 425.9 plus lambda naught m of NaAC is given as 91. So 91 minus lambda m naught of NaCl is 126.4. So 126.4 in the negative. Okay, now you just have to add or subtract this equation, and it will become equals to 390.5 Simon centimeter square mole inverse. Okay, so this is the answer for calculation of the lambda m naught for the acetic acid. Okay. Okay. Our next example is example 2.9, which says that the conductivity of this much concentration acetic acid is this. Calculate its dissociation constant if the limiting molar conductivity for acetic acid is this. So, when you solve it, you can use this formula of the limiting molar conductivity and kappa and the concentration, because concentration is given, conductivity is given, and limiting molar conductivity you have to calculate. But okay, limiting molar conductivity you have already given, and you have to calculate the dissociation constant. So first of all, let's find the molar conductivity for the acetic acid. So this will be kappa by C. So kappa is the conductivity, which is 4.95 into 10 to the power minus 5, divided by the concentration, which is 0.001028 mole liter inverse. You multiply it by 1000 centimeter cube by liter for the unit conversion, and this will become equals to 48.15 Simon centimeter square mole inverse. Okay, this will be the value of molar conductivity. Now, you know that the degree of dissociation equals to the ratio of molar conductivity and the limiting molar conductivity. So, we have both the values. We just put it in the fraction, And when you solve this 48.15 divided by 390.15, you will get the degree of dissociation as 0.1233, right? For the acetic acid. Now, the Ka, that is dissociation constant, will be C alpha square upon 1 minus alpha. Okay, so concentration you know, already given in the question. Okay, alpha we just have derived by the fraction of lambda m and lambda naught m, right? We have derived. So, we can also write the Ka in this term, in the limiting molar conductivity and the molar conductivity term. Okay, and using that you can write the Ka for the acetic acid as C, concentration given as this much. So we put this value here, multiply by the alpha square. Alpha we just have derived by using the del m and del m naught, which is 0.1233. We take the square of this divided by 1 minus alpha, so 1 minus this alpha terms. We just have simplified. Now, when you solve this fraction, the Ka or the dissociation constant will become equals to 1.78 times 10 to the power minus 5 mole-liter inverse. Okay, so this will be and this is how you can use the different formulas you have just learned in this lecture. Like for the dissociation constant, as you see in this question, and the degree of dissociation, the limiting molar conductivity and the molar conductivity, and the Kohlrausch law. Okay, for the calculation and for the practice of more questions. Okay, thank you very much for joining this session.